Colton, can I just ask, do we
Yeah.
get faster by just like simply memorizing everything? Like, is that the trick?
So, like, there is like a simply memorizing, but that I think only gets you like half of the way there, because like it's also like knowing what are the stumbling blocks. Like knowing at a tetrahedral intermediate, okay, what's the best leaving group? What are we trying to make leave? Do we need to do any protonations, deprotonations to get there? Are we in acid and base? And like the more you know the contours of those questions, the more like the faster that you're gonna get. Because like when I see an ester in a reaction for y'all, I'm like, okay, are we doing CADs? Are we gonna do reduction or are we doing double addition? And like immediately my head's just there because I've seen those practice and done it. And like that's not necessarily memorization as much as it's like memorization and the practice and contours. It's also a thing of like y'all have been doing organic chemistry for like 2 months, and I've been out here for a decade. Oof, oof, oof. But without further ado, welcome to section number 7. Woot. Guess who got their act together and has nice little section notes that are posted on Canvas? So sorry about the previous 2 sections. Honestly, it's because there were a lot of changes in the delivery, and it would have taken me many, many, many hours to change a lot of those. Whereas this one, it only took me like 3 or 4 hours. So I was able to kind of reuse a lot of it. But one of the announcements that I was saying right before I started recording, or I started getting into, was after y'all have your second exam scores back, either next week or the week after, I'm going to try to set aside some time to do one-on-one meetings for my section students. And that's anyone who is assigned to my section or like anyone who I'm regularly interfacing with. Like if you're one of the folks who like regularly comes to section or regularly watches my section videos or regularly comes to my office hours and like we have met. I would love to meet with you. I'll make a calendar and we'll do kind of like probably 10 or 15 minute meeting slots depending on how many people want to sign up for it. But I think I'm going to be sending the link out to my section students. And if you would like to do a meeting with me and you are not in my formally assigned section, please send me an email. That's going to be the biggest thing. So I just want to put that as kind of a disclaimer at the start of the section video and the start of section. Um, any questions before we jump into things for section proper? Also, no one's complimented my new haircut, but it's okay. It's okay. Moving on. So, for section today, we have 4 big sections, and substitution and elimination sometimes is taught over like multiple lectures and different classes, but really they are all part of the same game. We are talking about reactions that alkyl halides do, primarily. So, what we are going to do is we are going to talk about these 4 big reaction mechanism types of SN2, E2, and then SN1 and E1 we often group together. So, I'm going to kind of treat that as one chunk. And all of this is going in favor of building this GFP system that Serena talked a little bit about at the end of lecture. I know that that was like 2 weeks ago at this point, so I'm imagining y'all know nothing. I'm going to start from scratch and give you kind of my treatment of the material. So, without further ado, let's talk about the first family of reactions, SN2. So, the broad idea here for SN2 is SN2 is a type of substitution reactions. And substitution reactions substitute a leaving group for another chemical group. So, in the SN2 mechanism, what happens is a nucleophile comes and does a, quote, backside attack on the carbon leaving group here. So we are going to be breaking a bond with a leaving group. We know if we break a bond, a sigma carbon leaving group bond, we are putting electrons in the sigma star antibonding orbital. And we put electrons into that antibonding orbital, the bond breaks, and now a nucleophile is added where that previous leaving group was. We call it an SN2 reaction, S for substitution, N because it's nucleophilic, a nucleophile drives this reaction, and 2 because it's a second order rate law, all the way back to your Gen Chem kinetics of 0th order, 1st order, 2nd order. The rate of this reaction depends both on your concentration of the nucleophile and on the alkyl halide, or the compound with the leaving group. Substitution reactions are not hard. Like, you can see this is one step. So the broad idea is not hard, but there are two kind of challenges with the SN2 reaction. One is going to be predicting stereochemistry, because these reactions are stereospecific. And the other one's going to be figuring out which molecules are good candidates for SN2. Like, when would an SN2 reaction happen? So let's start off with the stereochemistry. SN2, this backside attack proceeds through a mechanism where we have this transition state here, where we are forming our bond, the nucleophile is coming to attack, right as the bond to the leaving group is leaving. And we get this trigonal bipyramidal geometry here. Now, when that happens, when the nucleophile is coming in from this side, these three groups that are not really involved in the reaction, they go from fanning out on one side, so fanning out here kind of to the left, to then fanning out on the right. And it's because of this transition state. Now, when that happens, I think that she used the umbrella example, right? Like the umbrella going down and then kind of pushing it up. When that happens, oftentimes, and I would say, when I say often, I mean like 98% of the times, this results in an inversion of stereochemistry. Because often your leaving group is going to be priority 1. Like, imagine a bromine leaving group or an alkyl halide. That's going to be the highest atomic number pretty much. And then imagine some nucleophile coming and attacking. So imagine like a C triple bond N. Even though that's a C, you have 3 bonds to N for the substituents. Or imagine an OR coming and attacking. That's still probably going to be priority 1 on this molecule for most alkyl halides. So because our priority 1 went from being kind of on the right side to the left side, then if you do your stereochemistry assignments of R and S, you see that it goes from being R initially as a stereocenter to being an S stereocenter. Now, there are cases where we might not swap R and S stereochemistry, but we have never tested y'all on that. It's only really when the leaving group and nucleophile are not the same priority. And that's going to be pretty rare for intraorganic chemistry. So you should have a pretty gut association of SN2 inversion of stereochemistry. And if we were in person in a real classroom, this would be one of our Pavlovian conditioning phrases of SN2 inversion of stereochemistry. It's really this kind of immediate association of what's happening. So let's first start out with a little bit of practice here. And I'm just going to go through these with y'all. These are really simple practice. These are not formal section problems. These are kind of, they actually might be in the practice problems. They at least are for the summer class. So for this first one, our SN2 mechanism, we have NaOH. And remember, an Na or a cation, anything in the first column, is just covering up a negative charge. So we know that this is really OH minus. And it's going to do the backside attack. So it's going to put electrons into the sigma star carbon bromine, kick off the bromine. And then we have our OH added in spot. We've substituted. And technically we did kick off a Br minus, but oftentimes we don't care about her. Leaving group, she left. I don't care where she's going. Now that's easy mode. There's no stereochemistry involved because she's not a stereocenter. But when we do have a stereocenter, then we have a couple of options for how we can do this. So now our nucleophile is SCH3 minus, and remember our Na is just covering up a negative charge. And so drawing our mechanism, we can draw it and make it look like a really firm backside attack. But the way, it matters the destination of our arrow, not actually our path of the arrow. So you could have easily just done SCH3 minus over here and just done your arrow like this. As long as it goes to the carbon, you're good. The positioning of the arrow doesn't matter, just its source and destination. But if we are thinking about the full mechanism and kind of how it's going, then one way of drawing our product would be we have our SCH3 on the opposite side because it did this backside attack. And then these wedges and dashes stay exactly the same. So the CH3 is still on a wedge. The hydrogen is still on a dash. But now they go from being kind of fanned up to fanned down. And that would show our inversion of stereochemistry. You don't believe me? Oh, well then guess what we get to do? We get to assign R and S. Wow. So priority 1, priority 4, priority 2, priority 3, We are in normal mode. 4 is going away from us. We trace 1, 2 to 3. This is R. And over here, we trace priority 1. Then hydrogen's priority 4. Then we have 2 and 3. 1 to 2 to 3. Counterclockwise, and we're in normal mode. 4 is going away. We are S over here. So it didn't, in fact, invert the stereochemistry. So that is one option for how to draw your product. You literally draw the nucleophile on the opposite side and keep the wedges and dashes the same. Option 1. Another option, and it's going to be just a different way of drawing the exact same molecule. So I'm going to say this is way number 1 to draw the product. Way number 2 to draw the product is you are going to put the nucleophile in the exact same spot that the leaving group was in. So initially we had our I kind of down and at the bottom, and so we were going to put our SCH3 in the exact same spot. And if we draw it this way, then what we need to do is we need to swap our wedges and dash. So we're going to have hydrogen on the wedge and CH3 on the dash. We can check that this is going to be just a equivalent way of writing this structure over here. By doing our RNS assignment, we see 1, 2, 3. It's clockwise, but our 4 is coming out of the page at us. So we know it's that opposite day. So instead of being R, it is in fact still S. So these are 2 valid ways of drawing it, and either one works. Typically go with whatever's easier to you. And for me personally, this way is easier. Just putting the nucleophile in the exact same spot as the leaving group and swapping the wedges and dashes. Like, I find that I have to think less for that, just as long as you are doing one of these 2 methods to preserve that inversion of stereochemistry relationship. Last one's a little bit harder. So last one, we are thinking backwards. We have a product, and the product has a stereocenter. So this is after some substitution has already happened. So our original molecule needs to have some sort of leaving group. But then what nucleophile should we have for this molecule to get this product? Well, do any of these things look like nucleophiles? Not for SN2. Like, you've seen hydrogen nucleophiles and carbon nucleophiles with like Grignards for attacking carbonyls. But those reagents that we've used for attacking carbonyls, they are not fair play for this reactions of alkyl halides. You only know reactions of these things doing carbonyl attacks. So in this case, the only thing that really could be our nucleophile is our CN. And you have seen CN before, but she is going to be a common nucleophile in substitution elimination. And so if we wanted to cover up the negative charge, CN minus, we would write that up as NaCN. So that's going to be our nucleophile that we add. And then for drawing the product, we know that inversion of stereochemistry happened. So I'm going to use my option number 2 method, where I'm going to put my leaving group, which pick your favorite leaving group. Mine's bromine. Do whatever you like. Play your own kind of music, sing your own kind of songs. I'm going to keep my leaving group in the same spot as the nucleophile. And I'm going to swap my wedges and dashes. So I'm going to put my hydrogen here on a dash, and then I'm going to put my methyl on a wedge. And so we know that this is going to do an SN2 inversion of stereochemistry, and so the wedge and dash will change in this representation. And if we ever have any doubt, we can always check RNS assignment. I know I kind of plowed through those. Questions, comments, concerns. Could you do chlorine or iodine? Yes. Or you could do like a tosyl. You can be as creative as you want with your leaving group as long as it's a good leaving group. Other questions? Okay. So then let's talk about some other factors affecting SN2 reactivity. So we mostly have just talked about the stereochemistry here. When do SN2s happen? Well, there are 3 big factors that affect reactivity, but one of them is by far the most important. For SN2, the most important factor that affects reactivity is steric hindrance. So that really is the accessibility of our accepting orbital. So there was a nice image in lecture notes where they have a space filling model of looking at if we are attacking a methyl alkyl halide, a primary, secondary, or tertiary. But one way to think about it is if we are having to do a backside attack, our nucleophile needs to come in contact with this carbon, right, to make a bond with it. And if we are tertiary, we draw these as little lines, but we know that these are each methyl groups. This is like a big bushy tail on the molecule, and the nucleophile simply cannot get through to do an SN2 backside attack on a tertiary. So like SN2 fully will not happen for tertiary alkyl halides. For secondary alkyl halides, it's slow, but SN2 is going to be the best possible for methyl and primary alkyl halides. And it's just because the carbon right here is going to be more accessible because there are fewer things in the way. So again, this is going to be our biggest factor affecting SN2 reactivity, and like the other thing that you should have an immediate association with for SN2, aside from inversion of stereochemistry, is sterics. SN2 sterics, SN2 sterics. There are two other factors which really I'm just going to kind of leave up here for reference. So we can talk about like leaving groupability of how readily something leaves, and weak bases are good leaving groups, and then we can talk about nucleophiles being stronger or weaker. But we really do not test this a lot. Like I think it would be good to know the general kind of trend here, and to be able to. I would not even say that you need to know how to rank all of them exactly, but I think that you should feel comfortable thinking through that weak bases are better leaving groups. And then nucleophiles, maybe one thing I will say, we have this word nucleophilicity, which means how good of a nucleophile is something. And to be a good nucleophile, two things need to be true. You need to have a high energy donating orbital, because remember, nucleophiles are going to be the donors in a reaction. And then also, you don't want to be bulky. So in order to actually act as a nucleophile and do a reaction, it's like, can you get to the reaction site? And if you are bulky, you cannot. There are also some considerations with nucleophiles in terms of the type of solvent that you're in, but our class doesn't really talk about that much. I don't think Serenia really mentioned that. And so I just put this in kind of like as a bonus note for a little bit more information. Again, far and away, sterics is the biggest thing that you're going to deal with for SN2. One notable character that I want to introduce to you is Miss Tert butoxide. So she is notable because she is a strong base and a poor nucleophile. And you won't learn many molecules in this course that have that combination. So, strong base. She is a strong base because she is an OR minus. That's like approximately the same base strength as OH minus hydroxide. It's a negative charge on oxygen. So it's a good base. But we just said nucleophiles are, to be a good nucleophile, you can't be bulky because it's not going to be able to access the electrophilic sites as easily. And so with this tert butyl group, it is really, really bulky. And so it is going to be this kind of constant character for this lecture where it kind of subverts some expectations. So you would think a negative charge on an O, OR minus, would be a good nucleophile. But if it's terbutoxide, be gay, do crime, subvert expectations, she is a bad nucleophile. She also has several aliases. My favorite is Kotbu. And then there's like T. Okay. That's too much. I need to calm down. But I want her to be memorable for y'all because otherwise we'll get tricked. I don't want you to be tricked. That's really it. So she's going to come back. She's going to be a recurring character this section. Love her work. Here we are. So that's all for SN2 for now. And this is technically, or I say technically, there was a technical issue that I was trying to work out before so that I could do this thing. In the summer, when I'm teaching my sections in person, I have my whole setup. Oftentimes, we're covering a lot of topics in section, and we have to do a hard pivot, right? We have to go from one topic, and then quickly we are in a different land. And so to ease that transition, I've used a soundboard, and it has like transition sounds. But in order to do that, I have to stop sharing my screen. And so I'm wondering if you'll be able to hear this transition. So let's see. And hold on. Normally it's more seamless. So the E2 reaction. New topic. Broad idea here. This is an elimination reaction. So we need to eliminate our leaving group. And when we eliminate our leaving group and get it fully out of there, and we're not just substituting it with something else, we create an alkene. And that's going to be a really big deal for us because you're going to learn like 20 reactions that start with an alkene. I think that's either lecture 8 or 9. So she is coming. Making alkene, big deal. But our elimination reaction, where we are kicking off a leaving group, if we are making an alkane, we also need to kick off another bond. We need to eliminate 2 things so that we can have this double bond present here. So what the mechanism is some base comes along and it is going to go and deprotonate at this neighbor. So a couple of like nomenclature things. This is really like an old school, like they were using alpha and beta designations long before everything got super standardized. But remember when we were doing like amine, I talked about this position right next to amine as an alpha carbon. And that was the same thing for like a carbonyl. The position right next door was an alpha, and then the one further away was a beta. Well, it's a little bit different with alkyl halides. So with alkyl halides, we don't consider the carbon to be part of the functional group. With alkyl halides, the functional group is the bromine, and the alpha carbon, the one right next to it, is the one that the alkyl halide is attached to. And then the beta carbons are the ones that are one further away. Why do I say all of this? Why is this here? It's because there's a very specific deprotonation that needs to happen, and specifically, it's going to be taking away a hydrogen on the beta carbon. In other words, it's a beta hydrogen deprotonation. And again, our leaving group is over here, the carbon attached to its alpha, one more away is beta. So that is how we get to a beta elimination, or at least the words for the beta elimination. Ugh. Sorry, my cursor is doing a weird thing. Do you also, why? There she is. Okay. So again, just like SN2, she is one step. She is in and out. It's not going to be a long like acetal mechanism or anything like that. And when, at the end of the day for this reaction, when we have our alkene, we also have a leaving group, and then we protonated our base. Why is she called an E2 reaction? E, because it's an elimination. We kicked off our leaving group. And 2, because, again, it's a second-order rate law. The rate of this reaction depends both on your base concentration and on your alkyl halide concentration. So, just like there's this stereochemistry association with SN2 inversion of stereochemistry being the immediate association, there is a stereochemistry requirement for the E2 reaction. So I like to say the E2 is a little bit picky. Here, the requirement is this beta hydrogen has to be anti-periplanar to the leaving group. So let's break down anti and periplanar. Anti goes all the way back to Newman projections. So remember, in a Newman projection, if you have 2 groups on the different carbons, the front and back carbon, that are exactly 180 degrees apart, we say that's an anti-conformation. So we want the leaving group and hydrogen to be anti to each other. And then periplanar, the beta hydrogen, the beta carbon, the alpha carbon, and the leaving group all need to be flat in the same plane in order for this reaction to happen. Now, this seems like a lot. This is high maintenance. Why does all of this need to happen in order for us to actually get a reaction done? Well, it is because in order to kick off our leaving group and make this double bond happen, we see that the electrons that were in this sigma CH bond are the ones that kind of fold in and become the pi bond over here in the product, right? Well, what the molecule is going to do with this anti-periplanar orientation is it's going to make the electrons in this sigma CH exactly parallel to the acceptor orbital over here of the sigma star carbon leaving group. So imagine this is the accepting orbital where the electrons need to go in order to break this bond and do the elimination. And then by making these exactly parallel, it just helps the electrons kind of slide over and make this into a double bond. So like they do go through like a rehybridization. They in the product will become p orbitals here in the pi bond, but it really just sets it up so the electrons, all they have to do is slide right over and makes it as easy as possible. This kind of geometric constraint for the reaction is, I think, the first one that y'all are really learning about in organic chemistry so far. But if you go on to take Chem 27 with biochemistry, this is going to be a really common idea that comes back, that you will need a specific orbital overlap between some donor orbital and some acceptor orbital if you are doing a reaction within the same molecule. So, anti-periplanar geometry, I often abbreviate this APP, just because it's a mouthful. So it's something to keep in mind, and it's really something that's more prescient when your molecule is constrained in terms of being a ring, and so it can't rotate freely, or when you only have like one beta hydrogen. When you have a lot of beta hydrogens, then we'll kind of talk about that has its own challenges. But this geometry is something that we are definitely going to have to consider anytime we are doing E2. So, the main factors affecting the E2 reaction, because we said the challenge of this lecture is not the actual reaction mechanisms themselves, but when each of these different types of reactions happen. So, one is just the geometry here that we just mentioned, the anti-periplanar. It's really just kind of a reality check. For example, this is the alpha position, these are the beta positions. Are there any beta hydrogens? No, there are like methyls on the beta positions. There are no hydrogens present. And so if there are no beta hydrogens, you can't do an E2 elimination. So that's just kind of our reality check to keep us out of delusion. And then the second factor that affects E2 reactivity is base strength. So the stronger the base that we use, the more likely it is for an E2 reaction to take place. So our general benchmarks are a strong base is something that is as strong as OH- or stronger. Weak bases are the strength of water or weaker. And then fair bases are in the middle. And I will say, I'm remembering this now, these numbers are not your exact class numbers. Like I think we use 14 for water, and I think we use like 16 for alcohols. And then I think maybe do we use -2 or -3 for H3O plus? Does anyone remember those off the top of their head? No worries if not. Like I don't need the exact numbers here. Q, I think? Oh, 0. Wait, y'all use 0 for H3O plus? I don't know. Anyway. The big thing is just the relative strength. So if you have a negative charge on an oxygen or a negative charge on something less electronegative than oxygen, which means it's more uncomfortable with that negative charge, she's going to be a really strong base. She's going to be really, really reactive. And so these are going to really like to do E2 reactions. Then water is going to be our kind of cutoff for weak bases. And we don't really think of water as being a base. Like it can act as a base, but it's really weak. Like we drink it. We're made of it. So it's not going to be like super reactive. And then really, I would say just memorize the ones that are in the middle because they're super common. So like a neutral, like amine, a cyanide, or a carboxylate. Those are going to be the ones that are kind of intermediate in between our strong base strength and our weak base strength. And I think that the rest of them, like the strong bases and the weak bases, will be easier to remember, but people just get tripped up on these fair bases. Okay, last thing I want to say here is there's an important distinction for these reaction sets that I see students get confused about all the time between alcohols and alkoxides. So let's compare them. So if we had ETOH, we would say that is an alcohol. Alcohols are themselves weak bases. Alcohols, remember, are really similar in pKa to water. And so that's not going to be a good base. It's not going to deprotonate something really easily. But then more than that, alcohols are also poor nucleophiles because they are neutral here. Like if they were to go and attack something, then they would get a positive charge on it because then it's having 3 bonds. So not a great nucleophile. However, if we deprotonate it and we have OET minus, and remember when we write that we often kind of put an Na to cover up that negative charge, OET minus suddenly is a strong base. It is going to be equal in strength to OH minus, like hydroxide, classic strong base. And a negative charge on oxygen is going to be a high energy donor. It's going to be a good nucleophile. And so being able to correctly see reagents as alcohols, which are kind of bad at everything, and alkoxides, which are kind of good at everything, that's going to be an important distinction to make, and I think is often a point of confusion. Cool. Now, I'm going to keep on checking because there are even more features. So, what about when we have a lot of beta hydrogens? Ooh. So over here, this is our alpha position, this is our beta position, this is our beta position. Here we have 3 beta hydrogens. Here we have 2 beta hydrogens. We have a lot of different choices for who we could deprotonate and like what our products would be. And so, let's say we used kind of a smaller base. Let's say we used NaOET here. We would get a mixture of different alkene products here. So, the mixture here, we have different types of alkenes. If the alkene is in the middle of the chain, it's called an internal alkene. And if it's on the end of a chain, it's called a terminal alkene. It like terminates the molecule. And you are going to, broad strokes, get more internal alkenes than terminal alkenes. So this is going to be about 55%. You don't need to memorize these, but you should know the general trends, and I'll summarize it in a minute. And then the terminal alkenes are going to be about 25%. But then within our internal alkenes, we can have trans alkenes, which are put its biggest groups opposite each other, or cis alkenes. And we can ask ourselves which is more stable. Well, the trans alkenes are going to be more stable because there's less steric clash. Like over here, these hydrogens are going to be hitting a little bit with these hydrogens. There's steric clash when they're cis, whereas when they're trans, you don't have as much steric clash. And so the breakdown is going to be 41% trans and 14% cis. And that's how we make up our 55% here. So overall, we can kind of like generalize this. And I don't know that Serenia actually used this name, but this is a rule, and it's called Zaitsev's rule. More substituted alkenes are more stable. And by substituted, I mean something having fewer hydrogens on the alkene. So as we replace our hydrogens with carbons or different R groups, we make more and more stable alkenes. And because more substitute alkenes are more stable, that is why internal alkenes are more favored. The idea of like, well, why are the more substituted alkenes the most stable gets back to this idea of hyperconjugation, which I think Serenia did talk about. And we're going to talk more about hyperconjugation when we get to SN1E1. But the big upshot here is when we have a choice of beta hydrogens, we are going to generally follow Zaitsev's rule and form more substituted alkenes. And also, when I say more substituted, internal alkenes are more substituted because they could have a maximum 2 hydrogens on them. If there was a choice between having one with like 3 things on the double bond that are non-hydrogen, or having like 4 things on it, well, the thing with 4 things on it would be the most substituted, so it would be the most stable. And then if we have a terminal alkene, at least 2 of our hydrogens, at least 2 of the things on the double bond have to be hydrogens. In this case, we have 3. So we see that these 2 are more substituted than our terminal alkene. Cool. So our like upshots are we are going to favor internal alkenes over terminal, and also that trans alkenes are more stable than cis to minimize sterics. Now, anytime we have a rule in organic chemistry, we have exceptions. We have exceptions. Do we feel okay about this rule of Zaitsev's rule? We're forming our internal alkenes more, and then between cis and trans, forming trans more often. And again, I don't think that's going to use this word in class, but I think it's just helpful to call that a name, to give that concept a name. So once we have our kind of general rule, let's talk about our exception. So we can mess with our internal and terminal product distribution by using bulky bases. So if we use a relatively small base, like ethoxide, OET minus, then we are going to follow Zaitsev's rule. We are going to get primarily our internal alkene formed, 71% here. And we can call that our Zaitsev product because it's the more substituted one, what we would expect. However, if we use Bigay du Crime, Kotbu, we know that that is really bulky, right? And to form an internal alkene, you would need to get a deprotonation from a part of the molecule that's not on the very tippy end. So like, this is what we would have to deprotonate if we wanted to form this internal alkene. And if we are Kotbu and we are this large molecule, it's actually going to be easier for us to get something that's on the very end of the molecule because it is bulky. And so it changes our distribution, and if we use this bulky base, we get more of our terminal alkene, which is sometimes called the Hoffman product. And the guy that this is named after, Hoffman, Serena actually studied with him. I think she did her PhD under him, or took classes with him, which was kind of like a But again, primarily we are going to get our internal. That's the most common one. But when we use our bulky base, then we actually get more of our terminal product formed. And you don't need to know these names, Zaitsev or Hoffman. I just think it's helpful. Now, with this, I know I've thrown a lot of theory at you. There's one more thing I want to do with E2 before moving on, and it's going to be relevant for one of the problem set questions. So more so than other courses, Harvard really likes y'all to think about doing E2 reactions on a ring. And the reason that we like y'all to think about it is because it combines a lot of concepts, and really it's a way for us to bring back in chairs. So in order for us to verify that we have an anti-periplanar geometry on a molecule in a ring, we have to draw a chair structure. So you should be drawing some chairs for E2 on a ring questions on the problem set. So let's convert this into a chair. So I'm going to put this one here and this one here. And I'm going to put my bromine up and then my methyl down. And then I'm going to do the other chair version. Remember, we have our kind of high energy and low energy conformation for chairs. So this one is the one that's both of them axial. But then if we assign it slightly differently, if we make our yellow carbon here and our purple carbon here, what we get is the bromine is going to be up equatorial. And then our methyl is going to be down equatorial. So between chair number 1 and chair number 2, which one is more stable? That's a classic kind of exam 1 question. Which one's going to be more stable, having our substituents equatorial or having them axial? Ding dong, I'm seeing 2s in the chat. So this one is going to be more stable. Now, we have NaOH, so we have a strong base. So we're thinking, okay, let's do an E2. Let's find our beta hydrogens. So we know the position that's attached to the bromine is alpha, and then one away is beta. So my beta hydrogens I'm going to put in purple. 1, 2, 3. Okay. Over here we have alpha, then we have beta and beta. Here we have our hydrogen. Here we have our hydrogen and our methyl. So in both cases we have 3 beta hydrogens, and that tracks with what we've seen up here. But now let's check for that anti-periplanar geometry. So let's start out with our most stable chair. I'm going to label these hydrogens 1, 2, and 3. Which of these hydrogens do you think is anti-periplanar to our bromine over here? Anti-periplanar. Remember, to be anti-periplanar, it needs to look kind of like this. We need our leaving group and our hydrogen to be exactly 180 degrees. Well, does this look exactly 180 degrees? Like one up, one straight down? No. What about this? Does that look like anti? No. And if we did our Newman production along here, what we would have is the bromine is like this, and our two hydrogens in the back are like this. So they're next door. They're like gauche to it. So neither of them are anti. And then here, both of these are going kind of up. And so that can't be 180 degrees. So in this conformation, we have no anti-periplanar beta hydrogens. So can this conformation of the chair do an E2 reaction? No. So even though this is the most stable chair, it is not E2 reactive. Ooh, okay. But let's look over here. Of these hydrogens, I'm going to call them A, B, and C. Do any of these hydrogens look like they could be anti to the bromine? And remember, our anti is kind of straight up and straight down. Y'all are getting it. Exactly. If we were to do a Newman production looking along this bond, like blah, 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 the bromine would be straight up, the hydrogen would be straight down. And so we have exactly one hydrogen, beta hydrogen, that's going to be anti-periplanar to the bromine. And so this is the only one that can do the E2 reaction and do our kind of base coming along, deprotonate, push in, and kick off. And so we know that our double bond is going to be formed over here. So it's not going to be a double bond with the methyl. So our product from this is going to look like this. We didn't touch the methyl stayed where it is, and then we made our double bond on the other side. Now, if we were to just look at that and not think through chairs, this would look like a violation of Zaitsev's rule, right? Because, hypothetically, the other one that you'd think about making is an alkene that looks like this, correct? And like that's more substituted. You would think that this is more stable. But we know that that is impossible because there is no anti-periplanar beta hydrogen on this position. And so this whole Zaitsev's rule and like forming the most stable one only really applies when they're equally accessible options. But when we are in a ring, we have these chair conformers, and we only really have a couple acceptable ways of having this molecule sit. If we were just a non-ring molecule, these molecules could rotate freely and they could adopt an anti-periplanar conformation really easily. But because we are on a chair, we are constrained. And so the other thing I want to say is this chair is E2 reactive, but is less stable. And so what this means is, yeah, the molecule itself is going to mostly be sitting in this stable position, but if it wants to undergo an E2 reaction, it's going to have to go and invest energy and become this higher energy conformation in order to have an anti-periplanar beta hydrogen to do the E2 reaction. And generally speaking, for the most part, there are like one or two like weird cases where they might want you to think through. But if you're doing E2 on a ring, you want your leaving group to be axial, because the only way you can get the anti-orientation here is for your leaving group and your hydrogen to be axial. So that's kind of our upshot. For E2 on a ring, we want to place our leaving group axial, which is kind of counterintuitive because that has an energetic cost. Okay. Any questions on E2? SN1 and E1 reactions do substitution elimination just like SN2 and E2 do. But the big thing is both of these proceed through a carbocation intermediate. I think the way that Serenia grouped them in lecture is she kind of did both substitutions together, then both eliminations together. But I really like grouping SN1 and E1 together because they often occur together. Like when you have S1 as a possible reaction mechanism, E1 is also a possible reaction mechanism. And it's because both of these proceed through a carbocation intermediate. So the mechanism for this, compared to SN2 and E2, we said that those were one step. This mechanism is two steps. And the first step is the same for both SN2 and E2. Carbon is in a relationship with the leaving group, and the leaving group has been unhappy for quite a while. And so the leaving group just says, it's been real. I'm going to take my electrons. I'm going to go. And sometimes a breakup can be a positive thing. And so we are left with a carbocation because this carbon used to have 4 bonds, and now it is robbed of a bond. Sorry, I'm seeing a reaction that I did not expect, but I'm glad. Hopefully the cheesy chemistry jokes make it better. But we are left with a carbocation here because the leaving group is taking the children and leaving with its electrons. Now, when we have a carbocation, we know from doing our MO theory that this is an empty p orbital. And so once we have an empty p orbital here, this is an acceptor orbital, an excellent acceptor, one of the best accepting orbitals we've seen. And so if we wanted to do a substitution, at this point, a nucleophile would just go and attack the empty p orbital, and then we would have our SN1 product. Or we can have next door a hydrogen get deprotonated by a base. A base would come along and deprotonate this hydrogen, and that could form in and make a double bond, and then we have the E1 elimination product. So the rate determining step in this reaction, in both of these reactions, is the leaving group leaving. It takes a lot of courage to leave a convenient relationship here. But then, once you form the carbocation, super reactive. So the next part is super fast. Either way, we say that these are first order rate laws because this slow rate determining step only depends on the concentration of our alkyl halide. It doesn't depend on our concentration of the base or the nucleophile. So that is why they are 1, so like SN1 or E1. And then same other name things apply. So because they share that same slow step, once you get to the carbocation, really either of these could happen. And so we'll start to talk about a little bit of like how do we get one over the other then if both of them could happen. So the main factor affecting SN1 and E1 reactivity is carbocation stability because this is our slow step. This is the thing that's hard to happen. And so if we can form a more stable carbocation, we are going to be a better candidate for SN1 and E1. So what makes something a stable carbocation or a less stable carbocation? The name of the game is hyperconjugation. So hyperconjugation, to me, like my informal way of describing it, is hyperconjugation is kind of the reverse of induction. So remember we talked about induction as something next door that's electronegative, like a fluorine, kind of tugging the electron cloud away and towards that electronegative atom. Hyperconjugation, I imagine, is kind of leaning electrons towards something that wants electrons. So if we have a carbocation, this empty p orbital, this is a part of the molecule that really wants electrons. It's really electron deficient. And so we are going to look at the sigma bonds that are next door. And these sigma bonds that are next door can lean their orbitals a little bit closer to that carbocation. And these little interactions help to stabilize the carbocation. This is the hyperconjugation. It's also why we said that aldehydes are more reactive than ketones. Because ketones have this donation, hyperconjugation on both sides of the carbonyl that stabilize the carbonyl, making it less reactive. Whereas aldehydes, they don't have the hyperconjugation, at least on one side. And so there's less donation and stabilization there. So if we have a methyl carbocation, like a CH3+, we have no neighbors next door that can come and stabilize this carbocation, because the hyperconjugation donation, it's from a neighboring sigma bond. It can't be one of the sigma bonds that's associated with the carbon in the middle. Like, having a carbocation to me is like the carbon's house burned down or something, and the neighbors have to come by and support. It can't be the bonds that are in the house that just burned down, kind of like that. So hyperconjugation, if we are primary, we have one carbon neighbor that each has sigma bonds. And so you have 3 of these stabilizing hyperconjugation like donations going and stabilizing the carbocation. By the time we're at a secondary carbocation, then we have 6 donations. And then tertiary carbocations have 9 donations. That is actually pretty darn stable. The stability of a carbocation is a tertiary carbocation, I should say, is a really, really well-studied phenomenon, and is like, this is something that you can actually crystallize and get a structure that exists, whereas these are pretty fleeting, and like this doesn't really happen. So again, our whole thing was, if we can form a stable carbocation, the leaving group's going to leave faster, and we are going to be a better candidate for SN1E1. So we say that tertiary and secondary carbocations are our best candidates for SN1E1. And so these would come from a tertiary alkyl halide, where the leaving group just left and made our tertiary carbocation, for example. So hyperconjugation is one way that we can stabilize a carbocation. Another way is resonance. So even better than a tertiary carbocation are carbocations that have resonance. So one type is a carbocation that's next door to a alkene, and it has to be next door. It cannot be on the alkene, because again, then the call is coming from inside the house. We need it to be a neighbor resonance donation. So here we have a resonance structure that's going to look like this. In resonance, the way I like to think about it is resonance are your ride or dies. Your house burned down, my house burned down. We're taking on this together. We have the same burden. Whereas hyperconjugation relatively is a weaker effect. It's the, oh, your house burned down. They're there. It'll be okay. And like 3 little there's don't help, but like 9 is like your whole community rallies around you. Whereas resonance, these are your best friends who are taking on whatever loss with you. We also have a carbocation next to a benzene ring. There's a lot of resonance there. And carbocations next to something with a lone pair. So this can also do resonance. So all of these are going to be really great carbocations and be great candidates for SN1 and E1. Also, I know it's a little silly with the metaphors, but otherwise it's so dry. Like, I don't think that y'all want to hear me just talk about like, well, in the MO diagram, there's donation between, no. Someone's house burned down. It's all story. Okay, so that's kind of the basics of carbocation stability, and that is the main factor affecting SN1E1. We also, of course, have to think about stereochemistry, because nothing can be easy. So when we form the empty p orbital of the carbocation, we know that this molecule is going to be trigonal planar now. It's going to be sp2 hybridized, and we're going to have an empty p orbital above and below. And let's imagine we're doing our SN1, so a nucleophile is going to come and attack that p orbital. Depending on if the nucleophile comes and attacks from the top or the bottom of the p orbital, we will get a different stereocenter there. We will get an R version and an S version. So that's one thing to keep an eye out for SN1. You are going to get a mixture of R and S stereocenters, whereas for SN2, we said it was stereospecific. We are always going to have this inversion of stereochemistry. So that's one kind of big defining feature for the stereochemistry. Now, we say that there's always a mix, but again, exceptions all the time. We can mess with this. So like, imagine this molecule here. If the leaving group chlorine leaves, this is tertiary, it's a really stable carbocation, sure, blah, blah, blah. But now, if we think about this, is it going to be easier for our water nucleophile to attack the top or to attack the bottom? Well, on the top face of the molecule, we have these 2 things on wedges that are really bulky. And so because we have 2 things on wedges that are really bulky, it's actually going to be much easier for water to just attack from below. And so you'll get almost all of this as your product, where the OH is added on a dash, only the S stereocenter being formed. But again, I think that this is a little bit beyond y'all's pay grade. I don't think that you'd be asked to predict this. In most cases, you're just going to form both versions of the stereo center. So you would put like a little plus minus by your answer. Now, the other thing I said was when we are doing SN1 and E1 reactions, we almost always get a mixture of the products together. Like it's hard to just get SN1 alone or E1 alone. And also between SN1 and E1, SN1 is simply faster. Like it is faster for a nucleophile to just bump into the carbocation than it is for this neighboring hydrogen to line up with the lobe of the p orbital, and you have the donation and make the elimination. And so we almost always get a mix of SN1 and E1, and the default tiebreaker is that SN1 is favored. So if you were asked for the major product, SN1 is favored over E1, if that is going to be the good candidate. We can get more E1 product by increasing the temperature, and that's going to be kind of like a thermodynamic control. Again, not really covered for this class, kind of like solvent effects. But if you see other videos or other textbooks or things, they might make a bigger deal out of temperature. That being said, if SN1 wins almost all the time, how do we do E1 reactions? Like how do we have a safe and stable way of getting the E1 product? Well, we conk it. So this E1 predominated or E1 only product method happens with secondary or tertiary alcohols using concentrated H2SO4. And we often write concentrated as conc. And so what happens is our alcohol, if we use a really strong acid like concentrated H2SO4, we are going to protonate it and makes it OH2+. Now OH alone, horrible leaving group. We said leaving groups need to be weak bases, and this is a strong base. But if we protonate it, OH2, lovely leaving group. It is a really, really weak base, so it wants to leave. So our leaving group here, now that we have a good leaving group, it can just leave, and we form this tertiary carbocation. And now, at this point, this is where we could do like SN1 nucleophile attacks, or SN2, or sorry, we could do SN1 of a nucleophile coming and attacking the carbocation, or we could do E1 of a base deprotonating. But the only other thing that's left in our beaker is this bisulfate, this like conjugate base of a really strong acid. Now, we know that this is a strong acid, so this is a pretty weak conjugate base. So it's not even a very good base, but because of all the resonance on it and because of how bulky it is, she will never act as a nucleophile. So even though it's a weak base, it won't act as a nucleophile, so eventually it's just going to do the elimination option. It's going to do the E1 elimination. It's going to deprotonate a hydrogen next door and then make our alkene. And so this is a method for only getting the E1 product, because normally SN1 and E1 compete with each other. So just another strategy here. Last thing, before we go on to putting it all together, the GFP stuff, I want you all to be detectives. Take a minute. Which happened here, SN2 or SN1? And there are like 3 or 4 clues based on looking at this where you should be able to tell why it's SN2 or SN1. So I'm going to give you a minute or two to think, and then I'm going to ask people who have clues to tell me what your investigation has yielded. Because we know that there was a substitution. A bromine was here replaced with an OMe. But let's think about why one would be favored over the others. And while you are thinking, I'm going to have a chicken nugget. Okay. Who has a piece of evidence to bring to the court? Okay. Zara, great piece of evidence. So you noticed we have a plus and minus. We have a mixture of products. And this is going to suggest SN1, because we know SN2 is very specific. Okay, that's one piece of evidence. What are other pieces of evidence for why this would be SN1 versus SN2? Or if someone thinks that there's evidence for SN2, what is your evidence?
I was looking at the nucleophile that came in, and
Mm.
it's like also on a wedge, like the leaving group. So we didn't switch around the what's it called? The stereochem like we should with
So
SN2.
close. Remember, the plus and minus means we have this version on a wedge and we have the version on the dash. So sometimes it inverts, sometimes it doesn't. And that's exactly what Zara was saying of like that's consistent with SN1 because we have that MTP orbital where it could attack the top or the bottom. But there is something here with this nucleophile. So is this a good nucleophile? Is an HOME a good nucleophile? In the chat, no. It's a bad nucleophile. Remember our difference between alcohols and alkoxides. Alcohols are poor nucleophiles. They don't have a charge on them. In our good nucleophile chart, all of our good nucleophiles, for the most part, have negative charges. Things without a charge are like the worst nucleophiles that we have seen. So, because of this being an alcohol, we know it's a poor nucleophile, and that's going to be like less good at SN2. It's not going to be as good at SN2 because we don't have a good nucleophile.
Colton, can I ask a question about that?
Yeah.
So the situation in which like Na could cover up a negative charge
Mm-hmm.
when you're talking about the nucleophile. So like why wouldn't that apply here? Is that because you see OH?
Mm-hmm.
Okay.
OH is a covalent bond.
Okay. Gotcha. Thank you.
Anytime you see Na, it's an ionic bond. Yeah. So that's exactly it. Like, I mean, hypothetically, if you deprotonate the H on HOME, it does become negative, but that is having to change it into a different molecule. Whereas the NaOMe, you know that that's just a counterion. And so if you're in an aqueous environment, they're just going to naturally separate on their own. Like, there's not really much holding them together. The last piece of evidence, though, here for why it would be SN1 more likely, and the answer, plot twist, is SN1. It's carbocation stability. What do you notice about this carbocation? Resonance. So this is a benzylic carbocation. It can do resonance all throughout this ring and spread out that positive charge. So this is a excellent carbocation, which makes it seem like SN1 more likely. Good. Good work. Good work, detectives. So now, let's bring it all together. And because it's a bring it all together, I wish I had had a sound cue ready that was like an Avengers symbol, but I don't. So I'm just going to play another one from the 90s. That's from the TV show That's So Raven. So, our challenge, again, is not these individual reactions. The reactions themselves are pretty easy. The challenge is all of the starting materials that do these reactions look pretty darn similar. So how do we distinguish which one happens if we are given some conditions? And to do that, we use this kind of reductionist system that is actually really helpful. And like I've seen a lot of ways different textbooks and universities teach substitution elimination, and this is by far my favorite because it gives you kind of an algorithmic approach that I just think is really, really handy. So each time we are looking at reagents that could be doing substitution elimination, we are going to analyze it and we are going to give it a grade for how good or how likely is it to do SN2, how likely is it to do to E2, and how likely is it to do SN1 and E1. And the grades are either going to be good, fair, or poor. So for SN2, we said our big criterion is sterics. So it's going to be good if your electrophile is methyl or primary, fair if it's secondary, and it's going to be poor if the electrophile is tertiary. Remember, it's too bulky to get there. Or if our nucleophile is bulky, like BK2 prime, COT-BU. That's going to automatically make it poor, even though it is like an O- nucleophile. Then for E2 reactions, it's all about base strength. So it's going to be good if the base is at least strong as OH-, poor if the base is H2O or weaker in base strength, or fair if it's somewhere in the middle. And then for SN1E1, it's all about carbocation stability. So it's going to be good if the carbocation is tertiary or better, so resonance stabilized, fair if the carbocation is secondary, and poor if the carbocation is methyl or primary. There are also a couple of like quality assurance checks that you need to do with this system because, again, this algorithm can't encompass everything. So one of them is a nucleophile vibe check. Just check in with your nucleophile, ask yourself, is it something like an alcohol, which is not a very good nucleophile? That could bump things down a little bit. Or is it COT-BU and it's like automatically poor candidate for SN2 because it's such a bad nucleophile? We also have our E2 reality check. Is there a beta hydrogen? Can it be anti-periplanar? If no, then E2 is impossible. And then you are going to have some scenarios where you get a tie. So what happens if it's like good for two things? Well, if things are tied, then what you go with is kinetics. Which one is going to happen faster? So the general order is SN2 reactions are the fastest, then E2. And these are generally much faster than SN1 and E1 because it takes a long time for a leaving group to leave. And then we have SN1 is going to be faster than E1. E1 is going to be our slowest. And again, I have some fine print here and some other kind of warnings. But I think let's just get into it, ladies and gents and others. So what we are going to do is we are going to go through and rank each of these good, fair, and poor candidates for each of these three different types of reactions. So for SN2, the thing we care about is sterics. And it's the sterics of primarily our alkyl halide. So we look at this alkyl halide and we see this is primary. So we would think, oh, it's going to be good. But then we have to do our vibe check, so our nucleophile. Who is it? Is it a good nucleophile? No. It's BK2 crime. Bad nucleophile. It is bulky. And so it's going to knock us down from good, and it's going to make us a poor candidate for SN2 because we have such a bulky nucleophile. Okay. Well, then we ask ourselves E2 favorability. So E2, it's all about base strength. So COT-BU, that's like an OR minus. Is that a good base, a fair base, or a poor base? Well, OR minus is about similar to OH minus in base strength. And this is the whole kind of classic thing about COT-BU. It is still a good base because basicity is about thermodynamics, but it is a bad nucleophile because nucleophile is about kinetics. So this is going to be a strong base. So it's going to be a good candidate for E2. For SN1 and E1, it's about carbocation stability. So the carbocation that would be formed is a primary carbocation. Now, I mean, we do have this double bond nearby, but if we formed our carbocation, can this carbocation undergo resonance with that alkene? No. And the reason why not is because this carbon that's in between them is sp3 hybridized. And so remember, we need uninterrupted p orbitals in order to have delocalization. So we would say that this is a poor candidate for SN1E1. So now we can look at the rankings. There's a clear winner. This is going to do the E2 reaction. And so we have our alpha position, our beta position. We know we are going to deprotonate one of these, and our product is going to be this. We formed an alkene. We eliminated the bromine. This question does ask us to do the mechanisms, but to be so honest, I'm just not. Mostly because the mechanisms are easy. Like, all the mechanisms are 1 or 2 steps. You're going to be able to do that, and I would rather spend time on this, like, theory and practice with y'all. So, up next, we have an alcohol, so not an alkyl halide, and we have concentrate H2SO4. We're conking it. And if we conk it, we know we are in E1 land. So we can do our little ranking system. So this is going to be tertiary, so that's going to be poor for SN2. This is going to be a strong acid, so not a base, just not on the base scale, so poor for E2. And then, because it's tertiary, we'd form a tertiary carbocation, which is a great carbocation, a very stable. It has 9 different hyperconjugation donating effects. So we know that this is going to be an E1 elimination. And so our product, and students often will either try to add or delete a carbon here. Remember, we only have 3 carbons. So our product is going to look like this, where we've made a double bond because we did an E1 elimination. And we know that we get only E1 because we were doing this concentrated H2SO4. There's just no nucleophile in it that can act as a nucleophile and go and attack the carbocation. C and D. To be so honest, I hate this. I don't want to be here. These look heinous. We do our algorithm. Love our algorithm. So for SN2, what do we look for? Well, sterics. So let's look at our alkyl halide. That is a tertiary carbon. So is it good, fair, or poor for SN2? Well, tertiary, that's going to be poor. It's going to be really inaccessible. For E2, we look at our base strength, and we have OH minus. That's going to be a strong base. So we are a good candidate for E2. And then for SN1E1, we have a tertiary carbocation. And so we are also going to be a good candidate for SN1E1. So now in trying to figure out which one actually happens, well, we're going to have a mix, right? There always is going to be a mix and competition of these, but we want a winner. We want to decide what's our major product. And whenever we have a tiebreaker, we go based on kinetics. So E2 is going to be faster than SN1E1 because it takes a long time for a leaving group to leave. So we are going to do the E2 reaction. Okay, well, this is our alpha position. This is our beta positions. Does this beta carbon have any beta hydrogens on it? Well, I see 4 bonds already in the page. None of them are hydrogen, so no beta hydrogens over there. So we know that we are going to be forming an alkene over here. So what I'm going to do for drawing my product is we did not touch this stereocenter in the ring over here. And then we are going to be making a double bond. Ooh, wait, I missed. There's another beta position, right? Because alpha, these 3 betas are the 1 carbon, 1 away from it. So we could form a double bond here. So let me just draw out a couple of things. So we have one option where we form this alkene. That would be if we deprotonated from this beta carbon. Or we could form this alkene. And that would be if we deprotonated from this beta carbon. Now, all of these single bonds can rotate freely. So there's not going to be an issue of can it be antiperiplanar or not, because you can just rotate and make it antiperiplanar. So if we have the choice between, I'm going to abbreviate them, this and this, option number 1, option number 2, which one is going to be favored? Option 1 or option 2? Well, this is our Zaitsev's rule. And we said the fewer hydrogens, or the more carbons on the alkene, the more stable it is. Well, option 1 has 2 hydrogens. Option 2 only has 1 hydrogen. So option 2 is going to be more stable. We know we are going to be forming our double bond over here. But then we have one more decision to make, actually. And that is, do we want, I'm going to call this option 2A. Do we want to make it with our double bond going up like this, or option 2B with our double bond going down like this? And to answer this, we have to think it's a little bit more complicated than cis and trans, right? Like, we have something both on the top and the bottom over here. And so let's think about which one's bigger. Is this whole thing bigger, or is the methyl bigger? The whole thing was bigger. So if this is our bigger thing, we want to keep our methyl group on the other side as far away from the big thing as possible to make it as stable as possible. We don't want to bump into the bigger thing. And so we are going to actually favor our trans product, our trans internal alkene. And so that is the one that's going to be our major product. So this one's a little bit more complicated because we have so many options for beta hydrogens. The hard part for this one was actually not even figuring out that it was supposed to be E2. It was which one of these alkenes could be formed, because there are lots of regioisomers here. Any questions on these three so far? Because I know that there's like a lot of decision making that comes into this. And it's different from before we were introducing the ideas. Now we're like, let's put it all together. Okay. Moving on, we have something that looks very, very similar, but now we have NaOAC. And AC is short for acetyl. So Na we know is negative, hides a negative charge, so we have O minus. And AC is short for a carbonyl and a methyl, and that's called an acetyl group. And that's also the name like acyl transfers you saw in CAD reactions. So this thing, well, I mean, we've changed our leaving group to a bromine, but it's still tertiary, so it's still poor for SN2. But now, what's the base strength of this? Is that as strong as OH minus in base strength? No, this one's going to be slightly weaker. So this one's going to be a fair base. And to just see that on the pKa chart, remember we said our weak base cutoff is H2O, our strong base cutoff is OH. This, like carboxylate functional group, it's in the middle between this weak and strong base cutoffs that we make. So it's going to be a fair base. And then for S1E1, it's tertiary. So it's going to be a good candidate. Well, now, which one wins? Well, the one that's good, which is now going to be SN1 and E1. But it's tricky. So SN1 and E1, we always get a mixture. If we want one major product, who wins between SN1 and E1? Miss SN1 wins. She is just simply faster. So what we are going to do is we are going to do a substitution here. And our product is going to look like this. And I'm then going to put my OAC on. But remember, SN1, we are going to get both the retention version and the inversion version. Oh, that sounded weird. So we just need to make sure we put our plus minus here, because we know we are going to be proceeding through a carbocation with an MTP orbital, and we could have attacked from the top, in which case it would be on a wedge, or we could attack from the bottom, in which case it would be on a dash. Last one. Over here, we start ranking for SN2. So for SN2, we look at our alkyl halide. This is a secondary carbon. So we would say it is fair for SN2, but wait, Vibe check on our nucleophile. Who is it? It's BK Ducray. And so, dropped down to poor. Okay. Then, for E2, base strength, well, this is an OR minus. So, it's a good base. Or a strong base, I should say. People get really picky. Like, technically, you're not supposed to use strong and weak with nucleophile, and you're not supposed to use good and poor with base. It's supposed to be good and poor nucleophiles and strong and weak bases, but we don't care about that for y'all. It's just semantics. Last thing, the carbocation. So this would be a secondary carbocation. So that's going to be our fair option for SN1. Wow, they really said screw SN2. They said no SN2 for you. Only E2 and E1. So E2 predominates because that's the only good one. But wait, we have E2 on a ring. So what does that mean? What do we need to build? A chair. So we draw our chair structure. And we need to draw the version where our leaving group is axial. So I'm going to assign this position with our leaving group down to a down axial position. And the one counterclockwise to it, the methyl is going to be up. Okay. So then I just need to find all my beta hydrogens. So this is my alpha position, that's a beta position, that's a beta position. So we have beta hydrogens here, here, and here. Now of these 3 beta hydrogens, which one is anti-periplanar to our leaving group iodine? Ding dong. Chat, you have it. So the only one that's going to be anti-periplanar is this one over here. So we know that we are going to make our alkene on this side. It's not going to be on the side with the methyl because that beta hydrogen can't be anti-periplanar. So our product is going to look like, not that. Well, I literally did the exact opposite of what I said. This. And oh my gosh, I think that this is the exact same example that I used in my earlier. So it looks like both Chris and I had the same idea of like we were like we want the children to see this. They need to know. But with that, I'm going to go ahead and wrap up section things. So there are 2 more practices on the exam problems, or the section problems. And in the section video, I'm going to record a little bit more. I'm going to talk through it. These practice is thinking backwards. So it gives you the product and says, what are some reagents that we could have used to make it? And then we have some conceptual problems. So this one's on the section document. And then these are just some that I really like as examples because I think that they do tricky things. The last thing I want to make you aware of is I have a handout. So I used to call this page what to expect when you're expecting substitution elimination problems. But now I just call it the substitution elimination review sheet. I really just try to put all the key things on one page. And so like this is hopefully an easy reference to go back to as you're working problems. And then literally all of these are the most common things that I have taken off points on exams for over the years. So I talk about alcohols versus alkoxides. I talk about tert butoxide. I talk about resonance stabilized carbocations, E2 on a ring, having multiple beta hydrogens. I really try to cover the bases. And then I even talk a little bit about solvent and nucleophilicity versus basicity as just kind of like a little bit more info to help kind of explain it. So hopefully that will be helpful as you are working problems. If you are feeling a little overwhelmed by these problems, I would highly recommend trying out pages 5 and 6 in this week's practice problems, just because those kind of get your sea legs in terms of like just practicing some of this. And a lot of this GFP system is just going to be like rote practice and getting good at it. But yes, thank you for coming to section, and that is going to be all. I will pause the recording. Dear viewers, hi, hello. So when I pause the recording from the section video, I saw that the screen was kind of paused like this, and I'm hoping that did not mean that it was not recording my whole screen for the last little bit. But in case it wasn't recording my screen as I was talking through this, I'm going to put up the work here, and I'll just kind of give it a second for you to look at it and pause. Again, I'm hoping it was recording the screen at the tablet as I was talking. But in case it wasn't, this is the section that was missed. So feel free to pause here and look at it. Now let's talk through these last two practices, number 4 and 5. So let me see. I'll restart my little timer. Okay. So for practice number 4, we are thinking backwards and we are wanting to see how we could have gotten to our product. So looking at our product here, we see that we have a functional group present and it's not an alkene, so we know we did a substitution, either SN1 or SN2. And then because we only have one stereoisomer, we know that we did an SN2 here. Okay. Let's do the same process maybe for the other ones and then we'll fill in the details. So over here, we have an alkene. So honestly, we could have done an E1 or an E2. I think either one would work. And finally here at the bottom, we don't have an alkene. We have some functional group present in OH. And we see that we have a plus minus. That's our indication that we had a substitution, and specifically an SN1, because we got a mixture of stereochemistry product. So let's start off with our substitutions, because I just think substitutions are a little bit easier. Like, we have to supply whatever is in the final molecule, right? So in order to get a CN in our molecule, we need a CN reagent here. So specifically, our good nucleophile version of this is CN minus, which we cover up with an Na, NaCN. Now, we know that SN2, we are going to have inversion of stereochemistry. So for my starting material, I want to invert that stereocenter. So I want to put my leaving group on a dash. And for the leaving group, we can choose whatever good leaving group that we want. My favorite's bromine, so I'm just going to put bromine here. So if we have this starting molecule with a bromine and then we use NaCN, then our CN minus is going to do a backside attack, an attack from the top face, and then we are going to get this product, only that stereoisomer, stereospecific. Cool. For this third one, the substitution, so if we want an OH on there, we needed an OH to add somehow, but typically we don't want to use OH minus. Why do we not want to use OH minus for a substitution? Well, we don't want to use it because it's a good base. And if it's a good base, or I should say strong base, then it favors E2, typically. And so, instead of using OH minus, the other way to supply an OH is by supplying an H2O. So, to start us off, we know that we are going to do SN1. And so the carbocation that we are forming is this carbocation right here. There we go. This is a tertiary carbocation, but then also it's next to this benzene ring, and so it's stabilized by a lot of resonance. So given that it's a really stable carbocation, and that our leaving group leaves initially, we know we need to have a leaving group at that spot, but it doesn't really matter where we put our leaving group in terms of a wedge or a dash. So I'm just going to put on a wedge, but we could do or on the bromine on a dash like this. Either one works. So that the leaving group would leave, it would make our carbocation, which is planar, then it could attack either the top or bottom. That's how we get both enantiomers. Now for this middle one, let's think about it. So it kind of depends if we want to do SN2 or SN1. So, or sorry, E2 or E1. So, depending on what we do, we know that our leaving group has to either be on the top carbon or the bottom carbon, because those are the ones that are in the potential alkene. So I'm just going to draw both versions. I'm going to draw my bromine here, or my bromine here. And then we can do it either way that we want to, but there are some considerations. So the thing I like about this bad boy is there is only really one option for a beta hydrogen, and it's right here. So if we want to guarantee our product, honestly, that's probably our best option to do here with a base. And we can use whatever base that we want. I might use NaOET. You could even use kind of Kotbu. But we just need a base. Or if we had done this one, we have choices. So we could either get a beta hydrogen up here, or we can get beta hydrogens in the ring. And so because we have the option of forming potentially this alkene, we know we want to get some reagent that forms the terminal one only. And so this is where we would have to use that bulky base and do like Kotbu. And because Kotbu is so bulky, it's only going to form that terminal alkene, or it's going to primarily form the terminal alkene. So you could do it that way. A third way of doing it, so we could do this plus Kotbu. Third way of doing it would be we could do an alcohol and conk it. And this would be an E1 pathway. So the other one, the one that I put in the box here, and this one, these would be E2 pathways with a strong base, or we could have done an E1 pathway. We would not want to do an E1 pathway with this, just because it's not going to form a carbocation on a primary carbocation like that. So, cool. That's practice 4, predicting the reagents. Last one, practice number 5. What products could theoretically form under these conditions? Well, we have an alcohol, we're conking it. So I think that it's just, like, we know we're doing an E1 elimination. So our options for possible products, we could form our double bond there, or we could form our double bond here. And theoretically, either of those could happen. But we know this is illegal by Brett's rule. We cannot have a alkene, like a sp2 hybridized atom, on a bridgehead atom here. So we cannot make a double bond with a bridgehead atom. And so this is the only one that we are going to get. Now, these other ones aren't on the section handout, but I think that they're good. Just like how this one makes you think about Brett's rule, these all have some sort of trick to them. So for this, we're going to rank each of them with GFP. And yeah, we'll do that. So here we have a secondary alkyl halide, so it's going to be fair. And then for our base strength, we have OH minus, which is good. And for SN1E1, it's secondary, so it's fair. So we know we are doing E2, and lo and behold, it's E2 on a ring yet again. So when I draw my E2 on a ring, I need to make sure I'm putting my bromine in an axial position, and we know it's on a wedge, so it should be axial up. That means our methyl up is like this. So our beta hydrogens are here, here, and here. Now in this case, we have 2 of them that are antiperiplanar. That one's antiperiplanar, and that one's antiperiplanar. So we have a true choice. And since we have a true choice, we are going to use Zaitsev's rule. So we are going to form the alkene that's more substituted, which is more stable. So we are going to be forming the alkene that's down like this. We are not going to form the alkene that is like up here, because that is just less stable. Cool. And the only reason that we can do that on a ring is because we have choices. We have 2 potential beta hydrogens. Okay, next one. We're conking it. Now, do we want to conc our primary alcohol or tertiary? Well, the whole reason that we are doing it is in order to make a carbocation. So if we do our GFP ranking for SN2, it's going to be poor because this is tertiary. It is going to be poor because we are an acid. We're not even a base. So we have a good candidate for SN1E1. So we're going to protonate this, and the leaving group leaves. And then we get to this intermediate. That is this. Now, normally we expect E1. We would expect E1 if we're conking it, because we say we only have OSO3H minus in the mixture. We don't have anything that can act as a nucleophile. However, on this molecule, we have an alcohol on the molecule. The call is coming from inside the house. And so, because there is another functional group present, it is going to do an intramolecular SN1, even with conc. And again, it's this rare exception that because there is another functional group present, then there is something that can act as a nucleophile, even in concentrated sulfuric acid. And so this is going to form a 1, 2, 3, 4, 5-membered ring. And initially it's going to be a 5-membered ring that looks like this. Like these are the 2 methyls at carbon 1 here. 2, 3, 4, 5. And initially it's going to still have that hydrogen on it from right after it attacks. But then there's going to be just a final deprotonation step. And so this will be our final product. Our last one, we have a secondary alkyl halide. So, I mean, I'd almost bet that many of you would go like, okay, then fair. But then what are we doing over here with Mg? Wait, we're not even in substitution elimination land. Mg, that's making a Grignard. So we know that that's going to go to MgBr. And then if we have water, well, we know that a Grignard is a strong base. So all it's going to do is go and grab a hydrogen. And so what's our product? Well, we are going to have a hydrogen in that place. And that hydrogen we don't even have to draw in because of the CH bond. So we are just going to have a cyclopentane. We're going to make an alkane at the end of the day. So all of these questions, if I'm going to be so honest, should have probably felt like trick questions. They are a little bit more complicated than some of these more standard substitution elimination questions. And it's because each one of these makes you interface with earlier ideas in the course. So this one with Brett's rule, this one with E2 and like on a ring, this one with an intramolecular reaction, this one with Grignards as strong bases. And so you can easily see how like a simple framework or a simpler framework and these kind of rules for a substitution elimination can become a little bit messier, a little bit more complicated. That is why I would highly recommend going through, I've deleted them. I think it was in my section video though. I would highly recommend going through the practice problems, page 5 and 6. So that will give you some practice with some simple substitution and elimination practice just to get your GFP skills kind of honed before you start doing some of the more involved, more challenging ones. And if you want to see a video where I kind of talk through or present it like an answer key for page 5 and 6, you can look at my Chem E-17 section number 6 video from the summer on the YouTube page where this video is posted. Last thing I'll say here for the people who are still around at the end of the video is if you are a person watching the videos and you are benefiting from this and would like to have a meeting with me, I mentioned it at the very beginning, but I'll mention it here at the end. Feel free to send an email to me, and then when I send out the signups, I will make sure that you get the email to sign up for like a one-on-one meeting just to touch base about the class. Cool. Okay. Have a good evening, day, night, whenever you're watching this, and goodbye.